TechSolve Hub. Module Code. Module Title, Structural Mechanics 3. Alternative Assessment Type, 100%. Instructions. 1. Answer all questions. 2. Calculate your unique student constant, SC, using the formula below. It would help if you had this constant to ask all the questions. Let Sn equals your student number, and SU equals the sum of the digits of your student number. SC equals log 10, Sn/105 plus SU/10, to 4 significant figures. Show your calculation and write the constant at the top of the first page of your answer sheets. For example, if your student number is Sn equals 652,471. The sum of the digits SU equals 6 plus 5 plus 2 plus 4 plus 7 plus 1 equals 25, so your unique student constant is SC equals log 10, 6.52471 plus 2.5, equals 0.9554, 4 SF. 1. Figure Q1 shows a pin-jointed spring bar system consisting of 3 identical rigid bars of length L/3 that are strengthened by 3 torsional springs at the joints A, B and D with stiffness constants of KL2, 2KL2 and SC*KL2, respectively. The middle bar is further supported at the middle point C by a linear spring with a stiffness constant K. A vertical load P is applied at joint A, where the lateral movement is fully restrained. A. State the 2 independent displacements you will use to describe the unstable, deformed configuration of the system. Then, the lateral displacement at C and the vertical displacement at A are expressed in terms of these 2 displacements. 4 marks. B. Derive the total potential energy as the function of the 2 independent displacements. 7 marks. C. Calculate the 2 critical values of the applied load P at which equilibrium becomes unstable. 7 marks. D. Determine and sketch the corresponding unstable deformation modes of the system. 7 marks. Total 25 marks. P. L/3. 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 Figure Q1. EG 320, Structural Mechanics 3, Take-Home Examination. Student constant, SC, is calculated using the formula, SC equals log 10, Sn/105 plus SU/10, rounded to 4 significant figures. Given the student number, Sn, as 964,354 and the sum of the digits from the student number, SU, as 31, we have SC equals log 10, 964,354/105 plus 31 tenths, equals 1.105. Q1. A. Assume the displaced configuration is based on the 2 independent displacements, D1 and D2. The lateral displacement at point C is the average of D1 and D2. Assuming small displacements, the angles are defined as follows. Beta, beta, is D1 divided by L. Alpha, alpha, is the difference between D1 and D2 divided by L. Gamma, gamma, is D2 divided by L. These angles lead to the following rotational displacements. THETA1, theta1, is the sum of beta and alpha. THETA2, theta2, is the difference between gamma and alpha. The vertical displacement at point A, denoted as U, is calculated using the sum of the small angle approximations for cosines of the angles beta, alpha, and gamma. Using the small angle approximation for cosines, the vertical displacement at point A becomes a function of D1 and D2. B. The system's internal energy, U, is calculated considering contributions from beta, theta1, and theta2, and the displacement D1 and D2. This internal energy expression includes terms for beta, theta1, theta2, and the combination of D1 and D2. The external energy, V, is given by the product of the load, P, and the vertical displacement, U. The total potential energy is the sum of the internal energy, U, and the external energy, V. C. For equilibrium, the derivative of the total potential energy concerning displacements d1 and d2 must be 0. This gives us two equations to solve. The equilibrium conditions lead to a system of linear equations in terms of d1 and d2, which can be arranged into a matrix. For non-trivial solutions, the determinant of the stiffness matrix must be 0, leading to a quadratic equation in terms of the applied load, P. Solving the quadratic equation yields two critical values of P, which are 5.2231 kL and 15.5736 kL. D. For the first buckling mode, V1, substitute P1 equals 5.2231 kL into the equilibrium equations to solve for D1 and D2. The result is D2 equals 1.4975 D1, indicating the mode shape. For the second buckling mode, V2, substitute P2 equals 15.5736 kL into the equilibrium equations to solve for D1 and D2. The result is D2 equals minus 0.2519 D1, indicating the mode shape. Sketches of the corresponding unstable deformation modes of the system would illustrate these shapes visually. Turnover. 2 Figure Q2a shows a propped cantilever beam structure of length 5 m subjected to 2-point loads at the positions shown. The frame has a uniform, non-standard Z-shaped cross-section, as figure Q2b illustrates. Assume that the yield stress of the frame Y equals 350 MPa. A. Compute the second moment of inertia of the cross-section, I. 2 marks. B. Determine the elastic modulus and the yield moment of the cross-section. 2 marks. C. Determine the elastic modulus and the plastic moment of the cross-section. 2 marks. D. Calculate the shape factor of the cross-section. 1 mark. E. Use the statistical or mixed method to find the critical value of P that causes the plastic collapse of the frame when A equals 2m. 13 marks. F. Now assume that A is changeable. Using a trial and error method, determine the critical position A, within an accuracy of 0.1 m, that results in the smallest plastic collapse load P. 5 marks. Total 25 marks. SC * PPT. A. B2. B. H equals 0.20 MT equals 0.02 M B1 equals 0.12 M B2 equals 0.10 M. T. Figure Q2. Dash. Q2, A. To calculate the second moment of inertia, I, of a cross-section. 1. Divide the cross-section. Break the complex cross-section into simpler shapes whose moments of inertia can be easily calculated. 2. Find centroids, determine the centroid of each simple shape. 3. Calculate areas, find the area of each simple shape. 4. Overall centroid, use the individual shapes' areas and centroids to find the entire cross-section's centroid. 5. Individual moments of inertia, calculate the second moment of inertia for each shape about its centroid. 6. Parallel axis theorem, adjust these individual moments of inertia to account for their distance from the overall centroid. 7. Sum up, sum the adjusted moments of inertia of all shapes to get the cross-section's total second moment of inertia. Dash. Q2, B. To determine the yield moment of the cross-section. 1. Find maximum distance, identify the furthest point in the cross-section from the centroid. 2. Use yield stress, given the material's yield stress, calculate the yield moment. This is done by multiplying the yield stress by the second moment of inertia and dividing it by the maximum distance. 3. Elastic modulus, calculate the elastic section modulus, the ratio of the yield moment to the yield stress. Dash. Q2, C. To find the plastic moment and plastic modulus. 1. Locate equal area axis, EAA, find the position in the cross-section where the areas above and below this axis are equal. 2. Calculate forces, determine the forces in each part of the section based on the yield stress. 3. Find lever arms, measure the distances, lever arms, from the EAA to the centroids of each part. 4. Compute plastic moment, multiply each force by its lever arm and sum these products to get the plastic moment. 5. Plastic modulus. Calculate the plastic section modulus by dividing the plastic moment by the yield stress. Dash. Q2, D. To determine the shape factor. 1. Calculate shape factor. The shape factor is the ratio of the elastic modulus to the elastic modulus. 2. Interpret shape factor. This factor indicates how much more the section can resist bending in the plastic range compared to the elastic range. A higher shape factor means the section is more efficient in the plastic range. Dash. Q2, E. To determine the critical load for plastic collapse using the statical method. 1. Bending moment diagram. Draw the bending moment diagram for the frame under a given load. 2. Plastic hinges. Identify potential locations where plastic hinges could form when the load reaches the plastic moment capacity. 3. Degree of indeterminacy. Determine the degree of indeterminacy of the structure. 4. Equilibrium equations. Use these equations to find the bending moments at critical points. 5. Plastic collapse load. Calculate the load that causes plastic hinges to form so that the structure becomes a mechanism, leading to collapse. Dash. Q2, F. To find the value of distance A that results in the smallest plastic collapse load. 1. Expression for moments. Express the bending moments in the frame as functions of A. 2. Critical load as function of A. Derive the critical load for plastic collapse in terms of A. 3. Trial and error. Test different values of A within the allowable range. 4. Minimize load. Identify the value of A that results in the lowest plastic collapse load. 5. Verification. Ensure the selected A is within the specified limits and leads to the smallest collapse load. Dash. 3. Consider the portal frame illustrated in figure Q3. The frame is subjected to 2-point loads, P1 and P2, acting at the middle points of the top and left members, respectively, as shown. The two vertical members have a plastic moment capacity MP, while the horizontal member has a plastic moment capacity SC*MP. Use the virtual work method to answer the following questions. A. State the total number of possible collapse mechanisms, including independent and combined, and state how many mechanisms can be skipped without affecting the calculation of the collapse load. 2 marks. B. Identify all possible collapse mechanisms that cannot be skipped and calculate the corresponding collapse load combinations of P1 and P2. 10 marks. C. Plot a graph with P1 against P2 showing the region of safe load combinations and the failure envelope. Further, find how many load combinations with 2 possible collapse mechanisms. 8 marks. D. Determine which mechanism causes the plastic collapse when P1 equals SC*P2. Further, check whether the yield condition is satisfied by sketching the corresponding bending moment diagram with key bending moments marked. 5 marks. Total 25 marks. 3M. Figure Q3. Q3. A. The total number of independent mechanisms is found by subtracting the number of redundants from the total number of possible plastic hinges. There are 6 possible plastic hinges. The number of redundant is found by subtracting 3 times the number of frames from the total number of restraints. Here, the number of redundants is 3. Therefore, the number of independent mechanisms is 3. There are 3 independent mechanisms. 1 top beam mechanism. 2 side beam mechanism. 3 sway mechanism. Additionally, there are 4 combined mechanisms. 1 top beam and sway mechanism. 2 side beam and sway mechanism. 3 top beam and side beam mechanism. 4 top beam and side beam and sway mechanism. Mechanisms 3 and 4 can be skipped because no hinge rotations are cancelled when combining mechanisms 1 and 2 or mechanisms 1, 2, and 3. The collapse loads for these combined mechanisms will be between the maximum and minimum of the individual mechanisms so that they can be skipped in the calculation. B. 1 top beam mechanism *. The equation for the collapse load is given by multiplying the displacement by the load and equating it to the sum of moments multiplied by their respective angles. The final load for the top beam mechanism is 2.8067 times the plastic moment. 2 side beam mechanism *. Similar to the top beam mechanism, the collapse load is found by equating the work done by the load to the energy dissipated by the plastic moments. The final load for the side beam mechanism is 2 times the plastic moment. 3 sway mechanism *. The equation for the collapse load considers the sway mechanism and equates the load's work to the plastic moment's energy. The final load for the sway mechanism is 2 times the plastic moment. 4 top beam and sway mechanism *. The combined mechanism considers both the top beam and sway mechanism. The equation involves the sum of moments and loads for both mechanisms. The collapse load equation combines the loads and moments from both mechanisms to determine the total load. C. To plot the graph of P1 against P2 for the top beam and sway mechanism. When P1 is 0, P2 is 3.105 times the plastic moment. When P2 is 0, P1 is 4.14 times the plastic moment. The graph shows two load combinations that correspond to two possible collapse mechanisms. These critical load combinations are labeled as C1 and C2. Critical load combinations *. 1 when P2 is 1.5 times the plastic moment, P1 is 2.14 times the plastic moment. The ratio of P2 to P1 is 0.7009. 2 when P1 is 2.8067 times the plastic moment, P2 equals the plastic moment. The ratio of P2 to P1 is 0.3563. D. When P1 is 1.105 times P2, the ratio of P2 to P1 is 0.905, which is greater than 0.7009. This means the plastic collapse will occur due to the side beam and sway mechanism. Yield conditions and bending moment diagrams. To develop the side beam and sway mechanism, 4 plastic hinges are required at specific frame positions. The bending moment diagram is checked to ensure the yield conditions are satisfied at all critical points. The yield conditions ensure the bending moments at specific points are less than the plastic and scaled plastic moments. This confirms that the side beam and sway mechanism is the actual plastic collapse mechanism for the structure. 4. Consider the framework shown in figure Q4. The frame is subjected to 2-point loads. The plastic moment capacities of the 3 members of the frame are MP, 2 MP, and 3 MP, respectively, as shown in the figure. A. Choose a set of internal and external reaction forces to draw the bending moment diagram of the frame and express the bending moments at some key positions in terms of these unknown reactions. 15 marks. B. To determine the true plastic collapse load P of the structure, assume the locations of some plastic hinges and show that the yield condition is satisfied. 10 marks. Total 25 marks. 4 am. Figure Q4. In question 4, part A, we label positions on the frame as AE clockwise. The degree of indeterminacy is calculated to be 1, indicating the structure's static indeterminacy to the first degree. To address this, we replace the roller support at E with a vertical reaction force at R, rendering the structure statically determinate. We construct bending moment diagrams for the original structure and its equivalent when loaded by analyzing the bending moment at key points. Part B involves finding the unknown variables P and R. We determine their values by introducing plastic hinges at various points and solving the resulting equations. The plastic collapse load, PC, is derived from the minimum calculated P value. Substituting P and R into the bending moment diagram confirms that the yield condition is satisfied, validating the assumed collapse mechanism. End of paper.